Okay. So let's see. Let's suppose you have a function.
Mhm.
Okay. So how do you denote a function? Functions usually, if they're real valued, they eat a number and they spit out a number, right? So you might have like f(x) equals x squared or something like that, right? And the characteristic detail of a function is that you can graph it. And if you graphed this function, you would get something to this effect. Oh, I can't do straight lines. That's fine. You'd get something to this effect, right? So here would be f of x, and here would be x, say, as a graph. And you might have something like this. Okay. Now, the characteristic of a function is that, or the defining detail of a function is that if you draw a vertical line, it only goes through the function once, right?
Yeah.
Can't do it twice. Um, Let me see what just happened. Okay. Now it turns out um, many things in nature can be described by functions. Say, let's say I know um, where I am right now, and I want to know where I'm gonna be. So let's say I don't know, maybe you a common example is like someone might say, "What was the temperature today?" Well, if the temperature today was like I don't know 70 Fahrenheit, you might put that here, 70 degrees Fahrenheit. You might check what the weather is tomorrow and say that F just takes you from today's temperature to tomorrow's temperature. And maybe tomorrow you get 72 degrees Fahrenheit. So right here. And so in this case, there would be, oops, what just happened? It's acting like I'm trying to make a new slide, but I'm not. Uh, you could draw a line right here and a line here and then see where they intersect and then plot this point. And that would be part of your map. Right? So we're just saying, okay, what if today's temperature fully predicts tomorrow's temperature? Then I should be able to plot this as a function. And then, if I'm at 72, maybe I go back to 70. So let's say here's maybe 70, and then over here's 72. So I draw a line here, and I draw a line here. And I find the intersection. It's there. So my function has these 2 points in its graph. Okay? So if I start today's 70, I look at the bottom axis, I go up to the point on the graph that corresponds to that, and then I go over to here and see where it lands me. It lands me right at 72. And then I take that and I look at the x-axis again, and then I can tell what happens after 2 days. And it turns out I end up back at 70, and so I go back to 70, and I cycle. Right, this is a period two cycle. Does that kind of make sense?
Yeah.
Well, okay. So this supposes that, everything is determined by the temperature and that there's no other details I need to know in order to know tomorrow's temperature. Of course, this isn't true in real life. It's much harder to predict the temperature than this. But many things you can measure have this behavior. They're functions when you plot how they evolve from one time step to the next. One example you might do is you might um, let me get rid of this. Actually, I can keep that plot. Make a new one. You might say, have a faucet that's leaking and it emits a droplet every few seconds or whatever. And you just say, okay, well, let's start by measuring how long the first droplet pair takes, but the time between the first two droplets. Let's say it's 2 seconds. So I'm going to say, okay, well, we get a sequence of inner drop times, right? So the inter drop times are sequence. I'm going to go like this. So the first one might be 2 seconds. The next one might be 3 seconds. The next one might be 2.8. The next one might be 1.2. Next one might be 4, and so on. Who knows? You just measure them and see what you get. But then you go and plot this stuff. So, I might say, well, let's take this to be x1. Let's call this x2, x3, x4, and x5, and so on. So x1 is the first time it takes between two drops, and x2 is the subsequent one. And we say, okay, well, let's plot xn here for any given n. And then necessarily, we'll be plotting xn plus 1 for the next one. So we're going to try to predict x2 given x1 and so on. So let's say 4 is right here. 4 is here as well. I'm going to draw a line to make this a little easier. So this should go to like that. Okay, seems good enough. And 3, 2, 1, and 0. You might be, say, here. Yeah, roughly. Okay, so what does this look like? I mean, all you do is just go to the first one, 2, and then write that it sends you to 3. You then go to 3 and see that it sends you to 2.8, so somewhere around like right here. You then go to 2.8 and see that it sends you to 1.2, somewhere around right here. A little bit too high. Oops. And then 1.2 sends you over to 4, so somewhere around right here. And quite often, what you'll find is that these maps end up, even if you have unpredictable behavior, these maps almost always end up being nice continuous functions. So you might end up with some kind of plot that looks something like this. Uh, oops, not quite. Or, it may go down further. Who knows? But you'll get something that's continuous almost always. Now, let's say I want to know, I've done a lot more experimentation. I figured out that the points tend to fall along this contour, this graph. So I've got this nice function. Um, so how do I actually run iterates of this? How do I use this function to predict the future? Well, let's say I started with 2.5 for a time that I observed, and I want to know what I'm going to see after 5 more drop wait times. So let's say it starts at 2.5. Well, I go up to see how high it is. And I map that over to here. Okay, then I need to map that over to this axis. So it's now here. This seems kind of annoying because I have to eyeball it, right? Do you know how I might make this more efficient?
Wait,
Like
you said
taking
oh, go on.
Um,
Uh,
so what I'm trying to do is I'm trying to say, okay, I've mapped here up to the function, then I've gone over to the y-axis. Now I need to take the y-axis's height and map that back onto this thing, the x-axis, to see what my next iterate's going to start at.
mhm,
So, instead of eyeballing it and saying this looks like roughly where I was on the y-axis, there's a trick I can use. Because, now I'd have to go up and I have to go to here and then say, let's map this over to the y-axis. And then I'd have to eyeball that and say, well, it looks like it's roughly right here, and then map that up and so on. Seems tedious. And it seems like it's prone to error. I can't be very precise with hand drawn computations. So there's a better way to do this. And that better way is to first draw a horizontal line, or a diagonal line, going through all the 1, 1, 2, 2, 3, 3, 4, 4 points and everything. So this is the identity line, or sometimes people call this a bisectrix. And I've not drawn it exactly right, but it's close enough. It's more accurate than I was getting before anyway. So originally I started at 2.5 for my first iterate. Oops, try not to do that. Um, so that was here. And I hate PowerPoint sometimes. So that's here. And I want to iterate that. So what I do is I go up to the function, and then I need to go left or right now because I just went up or down. So I need to go left or right to reach the red line. Okay. So I go left because that's the only way that it will take me to it. All right, I reached it. Now I stop. Now I need to go up or down because I've hit the red line by going left or right. So I go up or down to reach the black curve. Now I need to go left or right to reach the red curve. Oops, can't draw. Now I need to go up or down. I'll go there. I need to go left or right. Go there. I need to go up or down. Here. Continuing. Then you go left or right. Somewhere around right here. Maybe somewhere around right here. And then I end up on this periodic orbit, where I just go around this part again. Okay. This is called a cobweb diagram. All right. So does this make sense how I'm doing this? First, I get 2.5, then I iterate it, and I get roughly 1.8. And then I look at where I hit the red axis from there on out. I get something like 3.6, then I get something like 3.1, then I get something, or 3.2, then I get something like 2.9, then I get something like 1.4, then I get something like 3.9, and then I get something like 3.6, 3.2, 2.9, and so on. I just look at where I hit the red axis or the red line. And I
yeah, yeah, makes sense.
and you could use, a ruler and a level if you wanted to get accurate drawings. And you can do this by hand and it just works. Um, so this is called an iterated map, okay? Iterated one-dimensional map. And it's kind of interesting. Anything you want can be converted into one of these, like any kind of dynamical system. So one example of how to convert things into this kind of map to study other things um, is what's called a Poincaré map. So Poincaré is like one of the guys that was instrumental in figuring out dynamics and relativity theory and all this stuff. But let's say, let me think of an example. Let's say I've got, have you seen a Lorentz attractor before?
I have not, no.
Okay, let me pull a picture of it up. So it looks like this. And the idea is you're in 3D, okay, and you are in 3D, and you start by putting a point right here, say, and then what will happen is it will flow around, along these curves that you can clearly see. So it'd be right here. It'll flow around, and it will unpredictably cycle around. You won't be able to tell just from looking at the initial point how many times it'll go around. I mean, for the first few iterates, you probably can't just from how far away it is from the circle, but in the long run, it becomes chaotic. And this point versus one very close to it will behave infinitely differently after a finite amount of time. Like, not infinitely differently, but arbitrarily differently. They won't look at all similar after a few seconds. And they'll just cycle around, and then it flops over to the other wing, jumps over here, does a butterfly effect or a butterfly wing pattern. So this is a 3D map. Okay. Now, it's chaotic. You can't predict anything about it. However, if you put a plane right here, dead center, and you make it slice this thing in half, right? You can kind of see what I'm trying to draw, right? It's like,
Yep, yep, yep. Yeah, I see it.
okay. So if you put that there and you say, okay, well, I'm going to start on this plane, and I'm going to start by measuring how forward or backward I am along this depth axis. And
What
I
does it sketch a 1D iterative map on the plane?
Yeah, so I start with this sort of thing, and in particular, I look at initial conditions, which are like this. So I'm looking at it from this side, right, like this, and so that's my perspective. My eyeballs are right here,
Mhm.
and so I start right here. Here are my initial conditions, and I say this axis is x. It's really x is this, but I'm just going to call this x for now. Um, so this forwards backwards axis is x, and let's see, and I start a bunch of points along a particular line, and then I wait until they come back. So of course, they're going to cycle around, and then they're going to come back to here, somewhere on the plane, and then they'll pass through it, and then they'll either, you know, um, actually, maybe I'll take a different slice. So you could do it that way, and that one's nice, or you could take another slice, which is this right here, and you just put a plane up, and you say, okay, well, let's take a slice of points and let them evolve in time, and they'll go around, you know, and they'll come back and they'll hit somewhere. They may not hit exactly on the same line, but they'll hit the plane somewhere, and then they'll pass through, and then they'll go out. And what you do is you say, okay, well, where is it now? Project the result of where it ends up onto the axis again, then plot that as a point in a return map. So you have your bisectrix, and you might have something like for this one starts over to the left, so somewhere around right here, and ends up going pretty far to the right, so somewhere around right here. So that's the actual point. So if you start your trajectory iterating it as a cobweb, you'll end up here, and then it'll go to the right, and then you'll say, okay, well, where does this map? And they might go down to here or something. Who knows? But what you find is the return map that this will give you is the following. If I can find it. There's a photo of it, but it's kind of cluttered. Here we go. You would expect this to be really chaotic because it's so hard to predict these trajectories. right? Because they vary super widely. Like they're not similar to each other in any way. It looks like this. Okay. What does this tell us? It kind of tells you if I draw my bisectrix here. Oops, that if I were to start somewhere like right here at 36, which is probably in the diagram is probably right here or something like that. It would end up going over, oops, I've drawn it wrong. I would end up going to here, and then to the left, up, to the right, down, pretty far left, up, right, up, right, up, over here, down. Maybe a little bit to the left of that, so then it goes up, you end up over here. And if you let this keep going, it'll densely fill in the whole plot, and you'll never get something that becomes periodic. So this flows chaotically, even though the return map is really nice. Right, the geometry of it's super awesome, really clean. The flows are extremely unclean. So this is called a Poincaré return map. This is a really fundamental idea. You can take smooth dynamical systems and convert them into 1D maps. This is pretty powerful. You can use this tool now to study generally anything. You can study computer algorithms. You can plot times it takes you to run successive iterates of an iterative algorithm on a computer, and you should get a return map. And you should be able to study it and say it's chaotic and unpredictable or it's predictable. And I'm going to give you some tools to do that in just a second. But there's something absolutely fucking mind blowing about the way you study these maps, which I'll show you. So there's a basic result now you need to see, which is this. Does this example make sense?
Yep.
Okay, good. So let's say I've got my bisectrix, and let's say I have a map that looks something like this. Well, if I started here, then when I iterate to here, what's going to happen? What's my next point? I go to the blue curve, and then I need to go to the black curve by going left, the black line by going left or right. So in order to do that, I need to stay exactly where I am, but then I need to go up and down to go back to the blue curve. But I'm already there, so I don't go anywhere. So this, I would stay here forever. This is called a fixed point. So anytime your map graph passes through the bisectrix, that's called a fixed point. And if you land right there, you stay there forever. Now there are some analytical properties of these fixed points that we can determine, namely their stability. So one example is if I have perfectly flat uh, function, then if I have a fixed point right here, you can imagine I would stay right there forever. What do the nearby trajectories do? So one over here would go up to this curve, and then it would instantly jump over to the fixed point. Okay. This one would go right over here and then instantly jump to the fixed point and stay there forever. So if it's flat, it's stable. If it's horizontal, it's a stable fixed point because everything jumps to it instantly and stays there forever. In fact, this is called super stable fixed point. Um, if it's very close to flat, it's similar. So we might have something that's like this. So it's quite close to flat because it has a pretty small derivative at the fixed point. There's the fixed point right there. But nearby trajectories, say, go like this. One goes there, up or down, left or right, up, right, down, left, and it spirals in. So this is a stable fixed point. Likewise, if it passes from under to over, or sorry, hang on. If it passes from under to over, it's a little bit of a different story. But um, if you have a very steep derivative like this, that doesn't happen anymore. So here's the fixed point. But if you're nearby, you go far off and you don't quite come back, right? So this is unstable. And there's a nice analytical property that tells you what your stability is. So this graph is xn plus 1 as a function of xn. So it's future as a function of now. And stability is determined by this. Um, so the fixed point is at xn star, or x star, I should say. So that means xn plus 1 x star equals x star. So if you start at x star, you just stay there.
Mhm. Mhm.
So it's stable if this happens. The derivative of xn plus 1 with respect to xn evaluated at x star, the absolute value of it is less than 1. Okay?
Yep.
And it's unstable if the opposite is true. You may have seen this before.
It's been a while since I was in calculus, but yeah, my brain kind of auto-completed the ones.
Gotcha.
I think I have, but I don't know where I've seen it.
Okay. So this will be a little bit different from calculus. Also, hang on, my girlfriend's texting, being annoying right now. Caller. Okay. Hmm. So, well, there's edge cases. I mean, this is enough for us to study everything, though. I mean, even in the cases where the derivative is 1, we still have enough information to study. So let me just cover that case real quick. So, fuck, my foot's asleep. Shouldn't have gotten up. So what if dxn plus 1 over dxn, what if this is equal to negative 1? Or, sorry, 1. There's a couple of cases. There won't be any cases if my foot doesn't wake up again. This hurts. Give me 3 seconds. Okay, maybe more than 3 seconds. All right, the blood is coming back. Okay. So if it's exactly one, you kind of have that undetermined case where you don't know if it's stable or unstable a priori just from the derivative. And so you could consider higher order derivatives or one sided higher order derivatives. But just to give an idea of what's going on, this can happen in one of two ways. It can happen if it's flat like this, so it's in line with the bisectrix, or it could happen where it's a reflection of the bisectrix, like so. Now, if it's like this, then either you're peeling away like this parabolically, like you have some kind of quadratic tangency to the bisectrix, in which case, on this side, your one-sided derivative is for second order derivative or some higher order derivative, it is as if you were crossing like this over the bisectrix. So if your bisectrix were like so, then the curve acts like it's doing this sort of thing, right? Kind of makes sense. It's coming from beneath, in which case the derivative will have had to have locally been greater than 1, and so that part is unstable. So the trajectory will look like this nearby it, and it'll kind of go away, right, for the fixed point. On the other hand, the other side is acting like it's stable. So that side will be converging. Whoops. So that goes like this. And then it kind of asymptotically converges. On the other hand, you might have had the same thing from above, some kind of quadratic tangency, like so. In which case, this is acting like it's unstable. And so you go away. And this side is acting like it is stable because its derivative is locally less than 1. It's stable, sorry. So it converges to the fixed point asymptotically. And then for the non-parabolic uh, fixed points, tangencies, you might have this, right, where you cross over. Both of these are acting like unstable parts. So if you land here, you're going to go out. And if you land over here, you're going to go out. Okay. And vice versa for the other thing, where you're to this effect. This one, they're both going to be stable. Okay. So you can kind of just look at what it's doing nearby and say, okay, well, is it stable on that side or is it unstable on that side? Everything's pretty clear just from looking at a picture. If you're crossing from above to below, you can be stable or unstable, but if you're crossing from below to above, you're guaranteed to be unstable because you have to overcome this derivative of 1. So you have to have greater derivative than 1. Uh, yeah, pretty easy to reason about these things. No, this is kind of key because it says, okay, well, in order to study fixed points, all we got to do is look at nearby um, points on the graph. We don't care about things far away. We just need to know about the derivative and the higher order derivatives and maybe the shape of the graph locally, and we can figure out everything about the stability locally. This is a really key idea. Now, I want to consider something. Um, what about periodic orbits? What do they look like? So period 1 orbit is just a fixed point. So that says you have a point that literally lies on the bisectrix. So when you evaluate At that point, you just stay there. You don't ever move. That's period 1. Period 2. That would be 2 points on the bisectors, and they go directly to each other. So if I start here, I end up going right to the other one. So I need a point right here on the graph, and I need a point up here so that it looks like something like this. And we're assuming throughout all this that our maps are continuous. So my trajectory ends up looking like this. So I have a square for my cobweb. And I just go around that square over and over and over forever. Okay. And these periodic orbits are the fundamental thing in the study of 1D maps. And you'll see why in just a second. Period 3. Oops. What just happened? That would be you need 3 points. And maybe it looks like this. Okay. So your graph ends up looking something to this effect. Okay. Now, I want you to notice something. Can you draw a map that's continuous and has a period 2 orbit, but has no fixed point?
No,
Why?
because it has to cross over the bisectrix twice.
Why twice? This one didn't. That's a period 2 orbit. Now, the red line did, but I'm asking about the blue curve that actually generates the orbit, the graph, the return map.
So your question was, can you draw a period 4 or period
2,
2
2, 2, 2.
curve with no fixed point?
Right.
Let me think. So no fixed point would mean you don't intersect the bisectrix, or you don't.
That's right. That's right. The
You don't,
blue doesn't intersect it yet.
and it has to be period 2.
It has to have a period 2 orbit on it, yes. There have to
Mm.
be 2 points that generate back and forth oscillations.
Like x squared? Does that work?
Let's see. So x squared would do what?
No, it would have to be translated by some amount. X
Sure.
squared wouldn't work. Um,
So you're saying like take something like this.
uh, well, that would have a fixed point, right? So it would have to be facing upwards.
Okay. So you want a tangency or do you want it to actually go through?
I want it to go through, like just lay on the top half of the bisectrix.
Like that?
So something like that, yeah.
Oh, without the fixed point though.
Yeah, without the fixed point.
Okay.
Uh,
All right. So let's look at what the trajectories do. This one goes here, then you go to the right, you go up, you go to the right. This one also does the same thing. They all always go to the right. Because think, every point lies above the identity line, and so it's always going to be shifted to the right. Because the image, the output, is higher than the input. This is the input. This is the output. So you can't have a period 2 orbit because you can't ever decrease to go back to where you started. Makes
mhm.
sense? Okay. Now, another way to figure this out, and one that's kind of more fundamental, is this. Use deductive reasoning in a contradiction argument. So suppose that you did have a period 2 orbit, in which case you would have a cobweb that looks like this, up to some rescaling of your graph. Okay? And necessarily, this point lies on your function, and this does too. And by intermediate value theorem, so long as your function is continuous, it
Oh,
must
yeah,
pass
there's a
through
middle
here.
value. Yeah, yep, yep.
So it might go like this, but it still has to come back down and go through. Okay. So period 2 implies period 1. So if a map has a period 2 orbit, then it also has a period 1.
Can we generalize this for n to n minus 1?
Oh, yes, we can. But
Okay.
not like that. Not like that. It turns out that period 3 does, in fact, imply period 2, which, of course, means it also implies period 1.
Transitive? Is
Yeah,
it
yeah,
transitive?
that's
Okay.
right. That's a transitive result. But it also turns out that period 3 implies a period 4.
Okay.
And it also turns out that period 3 implies period 5. And it also turns out that period 3 implies period 6. And if you give me a number, it turns out that period 3 also implies that number. If you have period 3 orbit in your map, you have all periods. And it gets even stranger than that. You have numbers that don't even exist in the natural numbers that are admitted as periodic orbits in some strange sense, which is what we're going to talk about. This is the Sharkovsky stratification. And this leads to a very fundamental result in the theory of chaos in homoclinics, which nobody that I've seen except Sharkovsky himself has talked about. And he wrote a paper about this right before he died, but that's the only place I've ever read anything about it. It's super fundamental. So let's see. What else can we extract just from very simple reasoning? Because we actually proved this just now, right? We proved this thing using intermediate value theorem. Simple calculus. Well, if you have, let me think of how to say this. I'm not going to consider. Let's be clear about something. If I have a map that looks like, um, I have f of x plotted here, and I have x plotted here, and I have a cobweb with a period 2 orbit on it, and the graph might look something like this. Then it turns out that I can plot also a different function, which is f of x, or if you want, f of 2 of x, the second iterative of f and x. Now, it's necessarily the case that if I take this input value right here and I look right here on the other plot, that's got to be a fixed point of that map. And also, this one has to be a fixed point as well. So the graph of f applied twice has to go through these 2 points. And maybe it looks something like, let me think about where the middle one goes. Well, it also has to be a fixed point. And so the graph might look something like this. It's guaranteed to have those 3 points on it. Why is that?
IVT?
No. So think about what's happening. If I map this point into f twice, it's going to go right back to where it started because that's what I found when I found it's a period 2 point. It goes to here, then back to where it started after 2 iterates. Likewise, so that gives me this point. Likewise, this one starts here and then goes down. That's one iterate. Second iterate goes back to where it started. So that's a fixed point. And moreover, this point
Stays where it is. Okay, yeah.
after one iterate is where it was, and after the second is still where it was. Yep. So those are guaranteed to be fixed points. So what does this mean? Well, it means if I have a, let's call this a period 2 point. If I have a period k point, this implies that it's also a period mk for any positive integer m. So if this is a period 2 point, then it's also a period 4 point, period 6 point, a period 8 point, period 10 point, and so on. And we say that this is a minimal period, a point of minimal period too. Okay. It's the smallest n, so min period 2. 2 equals n smallest n such that f n iterates at that point equals x. Takes you back to where you started. So it's the smallest amount of iterates that it returns back to where it came from. This is a minimal period 1 point. This is minimal period 2 point. Okay. Does that make sense?
Mm-hmm.
Okay. So now we can speak about minimal periods. So this result, we're going to talk about only minimal period points, and this is going to help us not confound things. Now, let's see how far we can get simply on reasoning, just basic reasoning. If I have a map which has, let's say this is f of x, this is x. If I have a map which has a period 2 orbit, then it is also guaranteed to have a period 1 orbit, a minimal period 1 orbit. MP2, so if there exists one, that implies there also exists a minimal period 1. Agreed? By AVT.
Mm-hmm.
Now consider what happens if you look at the second iterate of a map, and that second iterate has a period 2 point, which means the original map has a period 4 point. Then, because this has to be continuous by composition of functions being continuous, then the period 2 has to have, uh, there has to be a period 2 fixed point. Period 2, minimal period 2 point. So what I'm saying is, if there exists a minimal period 4 point, then there also exists a minimal period 2 point by IVT again. Agreed?
Yep.
Okay. Now it turns out that if I write the following, let's see if I have space up here. Let me move this stuff up a little bit. We can generalize this for all n and get all the powers of 2 this way. That's really a nice result. So if I have f to the 2n of x on the y-axis, and I've got x on the x-axis, then it turns out that this happens. If I've got, I should not do that, I should write fn here. And I've got a period 2n, minimal period 2n orbit. Let's do that in blue. This has to be on there as well. So if I have a minimal period 2n orbit, this implies, by IVT again, that there exists somewhere. Not only does there exist one, but in fact, it lies within the period 2n cycle. So you can think of these as intervals on the x-axis. This one has to lie inside of it. Well, please stop throwing my screen around. Okay. So what does this say? Well, it gives us some kind of nice a start to our ordering of the natural numbers. So it's easiest to get a period 1 orbit. 1, that's implied by 2. That's implied by 4. That's implied by 8. That's implied by 16. That's implied by 32, and so on. Okay. And you get all the powers of 2 this way. Okay. Can we do more?
What about 3?
3? 3 is going to be the last one.
Okay.
So that's the hardest to get. You can look at 3. So if you have one that looks like it has a period 3 orbit in it, say like this, then it has to have a point here, here, and here. I've kind of drawn something that is in function. Okay. Now note, if it has this stuff, um, you firstly see that it has a period 1 orbit. Quite clear.
Yep.
Uh, I'm trying to think of a good way to reason about this. Sharkovsky, to show that this implies that all other period orbits appear as well, he just uses graph theory arguments and he labels these 3 points, this, and this. And he says, okay, well, in order to have a period 3 orbit, you've got to have this contortion thing going on. So, namely, you could have period 3 orbit this way that I've drawn it, or you could have it this way. And there's only 2 ways to have it. You could have the jigsaw pieces, like the little saw blades sticking down, or you could have them sticking up. It doesn't matter. So you have to choose one or the other. All right. So those are the only 2 choices. Now, they're both the same thing. They're just reflected, but they both behave uh, in a similar fashion. Let's see. Sort of. There's a transform that takes each case to the other without disturbing the dynamics. So you can just study this one, the left one. So if we just study that one, then well, what is it doing? It's sending this point A and B and C. It's sending A to B, and it's sending B to C, and sending C to A. Okay. So namely, A to B is getting. Let me see if we can extract the fact that it has a period 2 orbit in it. B to C. That is sending this over to here, this to here, and this to here. And so think of what's happening just with this part. So if you take B to C and you pick it up and you put it back kind of down and you put B here and you stick C over here, then these points were all originally contained in here, right?
Yeah.
Okay. And because the map is continuous, you're guaranteed that there's a fixed point of that. And you actually see that right here. So I'm trying to see why there should be a period 2 fixed point, period 2 orbit. But it follows from similar reasoning. So if you do this twice, what do you end up getting? Well, oh, okay, that's clear. So if you do this twice, you end up getting a map that does one more iterate of this permutation thing. So whereas you sent B to C the first time, now you're gonna send B to C. Whereas you sent C to A last time, you're gonna send C to A. And whereas you sent A to B last time, you're gonna send A to B again. So now the second iterate is going to be a map from ABC to CAB. And think of what that is. That is, hmm, that's precisely this. And so it's just a reflection of the thing that had a fixed point already. So you'll have a period 2 orbit that has some component in this part. You're guaranteed that by just a similarity argument. I could formalize it, but it's a little too tedious to do that right now. Hopefully, it's intuitive. Um, right, because you're sending that to C. Right, this goes over to here. You're sending B, this thing, to A, and you're sending C to B. So the second iterate of a period 3 orbit looks like you just reflected it to be an upside down period 3 orbit, basically. So you still have that fixed point of the second iterate map, and so period 3 implies that there exists a period 2 orbit, and so on. So I'll just state what the full stratification is, or the full Sharkovsky order is now. And you can use this kind of reasoning to get through the whole thing. There's no fancy tricks needed. It's all proven using a little graph reasoning and basic calculus. So Sharkovsky order is this. You have one. You can have a period 1 orbit in a map and nothing else. Quite easy. In fact, a map that has such a thing is just the flat horizontal map. Everything maps right to this periodic orbit, and there's no minimal period 2 orbits of any kind. Okay. And that, we'll say, is less than, I'm going to use this to denote, is implied by the existence of 2. Nothing in between these. And then you have 4, 8, dot, 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 through 2 to the n, whatever n might be, dot, dot, dot. And then I'm going to write this. Don't worry about what this means just yet. Um, okay. Now, at the other end, you have 3. This is the hardest one to obtain, and if you have that, you have all other numbers as minimal periods for some orbit in the map. Um, and just to go back for a second, in this map, I should have a period 2, and you should be able to draw it. So what would that look like? Well, I'm thinking something to this effect, right? Something like that. Okay. And you should be able to draw a period 5 and a period 7, 6, 8, 9, 10, so on. Hmm. Now, 3, the only one that's nearly as hard as 3 to obtain is 5. So it's possible to have a period 5 orbit, but not have any period 3 orbit. But it's guaranteed that if you have a period 5 orbit, you'll have all the other numbers. namely 7, is just about as hard as 5, but you can have period 7 orbit without having a period 5 orbit. And if you don't have a period 5 orbit, then you certainly don't have a period 3 orbit, because if you did, you'd have a period 5 orbit. Then 9, then 11,
Is it all
13.
primes?
No, you would think so, but no.
Oh my god,
All the
okay.
odds. It's
Oh,
really
I see.
strange. And then you have something even weirder, which is this. So this goes up, of course, through 2n plus 1. And then this goes down to something I call 2 infinity plus 1. And we'll see what these infinity things are in a second. But nobody's talked about this. I developed this notation, I'll say. This is my own crap. But most of the time people leave this part out. But they're missing part of the story if they do that. Well, what do you have after all this? After all the odds, what comes next? Because we haven't covered all the numbers. When does 6 come into play? When does 8 come into play? Whatever. Well, 8's up here, but what about 6, 10, so on? So it turns out that right after all the odds, you've got 2 times 3. Then you've got 2 times 5, 2 times 7, 2 times 9, 2 times 11, 2 times 13, 2 times 15, dot, 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 2 times 2 infinity, 2n plus 1, 2 times 2 infinity plus 1. Okay? Hopefully that makes sense. So you have 6. If you've got any odd, then you've got all the evens. That much should be clear because we have all the odd numbers here. So if you've got any odd minimal period orbit, you should necessarily have every even minimal period orbit possible in your map somewhere. It's guaranteed.
Mm-hmm.
If you've got 6, then you're guaranteed to have 10, then you're guaranteed to have 14, then you're guaranteed to have 18, then you're guaranteed to have 22, then you're guaranteed to have 26, then you're guaranteed to have 30, and so on for all the 2 times odds. And then also, before that comes 2 squared, so 4 times 3, so 12. 2 squared times 5, 2 squared times 7, and so on. That's 2 squared, 2n plus 1, and then 2 squared, 2 infinity plus 1. Okay. And then right after that comes 2 cubed times 3, and so on. This just keeps on going forever. And then eventually you hit 2 infinity. All right. So check and see if you agree that every natural number is in this list.
Yeah.
So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep, we got everything. Okay. Now, what's the point of this? There's 2 parts to this theorem. So theorem 1, forcing theorem.
Forcing theorem.
That is the theorem that you know already, which is if there's something higher in the so if you have a number in the Sharkovsky order and you observe a minimal period in your 1D map, your continuous 1D map of an interval, and it has a minimal period in this list, then everything that came before it. So say you have this, then everything before it appears in the list. Okay. All the natural numbers before. Of course, it doesn't mean anything to have this appear because that's not a number, right? The little things with infinity in them, those don't mean anything to us yet. But all the natural numbers that preceded in the Sharkovsky ordering, you do have them. You're guaranteed it. Theorem 2 is the following, and this makes the infinity things make sense. The realization theorem. Okay? So what this is take any interval or take all the real numbers. There exists a function mapping that interval to itself, which functions as a return map, a 1D iterated map. So, what is this realization theorem thing saying? It's just saying, I can pick any number out of this Sharkovsky order I've written down. I can pick anything out, even, like 8, 4 or something, and I can get a map that has that. And necessarily it has all the previous ones too, but it doesn't have anything greater. So this isn't in there. Likewise, this isn't in there. So I can realize any number as the largest Sharkovsky maximal uh, minimum period that shows up in the map as a orbit, a trajectory. And what does that mean for these infinity things? Well, it means I can find a map. For instance, if I look at this one, I can find a map which has all the stuff less than this, but nothing greater than this. So all this stuff is bogus. It's not in there. So I can get a map that has all the period 2 orbits in it, but nothing else. Period powers of 2. Okay. I can also get a map that has all but the odd numbers, and that would be associated with this 2 infinity plus 1. It has all the even numbers in it, but no odds. I can also get a map that has all the numbers that are not 2 times some odd, which that would be associated with realization of that, and so on. Okay. Right. It wouldn't include the odds either. It would be anything that doesn't have uh, 2 times an odd or 4 times an odd, or sorry, 2 times an odd or just an odd. Unless it's 1. One's the special case. You always have to have 1. So I can realize any map in accordance with the Sharkovsky ordering. Okay. So this is really fundamental because this says anytime I take any system or any kind of dynamics of any sort from any system whatsoever, physical, mathematical, doesn't matter. I can record data and write it down and come up with some quantity I want to think about return maps with, like enter spike intervals for a neuron or something like that. And it just so happens that it has to follow this theorem. Now, there's a couple of accompanying theorems which make this heftier in a sense, like they give it weight, they make it mean something to you. Right now, it probably doesn't mean much. It's just like, okay, there's numbers for orbits. Who cares? But it turns out this is extremely fundamental. Okay. Lee and York are 2 mathematicians who proved the following before Sharkovsky proved this result. Period 3 implies chaos. So if you have a period 3 orbit in your map, not only do you have all other periodic orbits of all periods, you also have what's called chaos. So what this is saying is if you have a period 3 orbit in your map, like so, you are also guaranteed to have uncountably many points in this interval inside the period 3 orbit that when you evolve them, they never converge to anything and they act chaotically and they're unpredictable. They have what's called positive Lyapunov exponents. So this wouldn't be it. It would be something like, let's look at the critical point. It's probably a good idea. Oops. So here, maybe. A little bit down from there. There we go. This should never converge to anything. And it'll fill this in, at least part of it, densely, in the topological sense. So you should have unpredictable behavior if you ever observe a period 3 orbit. There should be somewhere where you can get unpredictable chaos. This is with anything you can measure, ever. This is like you track how long reps on a bench press take you between every rep, like how long the one rep is versus how long the next one is. Study the relationship between. If you can find a period 3 uh, stable configuration of some sort, then you're guaranteed to be able to change the initial conditions to some setup in which you'll have chaotic, unpredictable behavior forever. Okay. Now, this is kind of the piss water version of what I have been looking at lately, which is um, there's this other notion in 1D maps called homoclinics. So homoclinic orbits. The idea is the following. Let's say you get a map with a fixed point in it. Okay. And it's possible to have, let's do this actually. It's possible to have a map that has this sort of setup. So firstly, I need the fixed point to be unstable. So I need to make sure it's pretty steep at the fixed point, right? Greater than 1 in absolute value for the derivative. So this works. It's possible. I'm going to draw in backwards time from this. I'm going to come here from somewhere. Well, I had to have come from over here, if not staying right where it was. So it's the only other pre-image. Let's say I came from here on the right side. I'm going in backwards time. These are backwards iterates, not forward. So I'm actually choosing to go to the rightmost branch each time. So what this is saying is, let's zoom in right here. I've got this bisectrix going like that. I've got the map itself going like this, and my trajectory is coming out from here and going outward unstably. What does this mean? It means that if I started right here, I would go here, and then go out to here, and then out to here, and then out to here. And it also means if I started right here, then I would go to here, and then I would do what I just did. If I started right here, sorry, that's the same as starting here. If I started here, I would go out to here, and then do the same stuff I just did. If I started right here, I'd go out and then do the same stuff I just did. If I started here, I would go out and do what I just did. So it doesn't mean anything that I go backwards and converge to the fixed point. It just means that, you know, this point has a pre-image which happens to be right here. And if I started here, I would have ended up here after one iteration. And if I start here, I end up here after one iteration. So in backwards time, it's possible for me to converge back to the fixed point. So there is a sequence of trajectories which all agree with each other. So I'm saying one of the trajectories is just this. Right? It starts here, goes up to the fixed point instantly, and stays there forever. There's another trajectory which starts here, then goes down to here, and then over to here, and then up to here, and then stays forever. There's another trajectory which starts here, goes up to here, like so, and then converges and stays forever, and so on. And there's a sequence of these going backwards in time that converge to the fixed point in backwards time. And this is called a homoclinic trajectory or a homoclinic set. And this is the fundamental tool in chaos theory. And nobody seems to know about this. I mean, yes, there's like people studying it, and there's isolated papers that dote very briefly on the fact that this is instrumental in chaos, but none really says why. And Sharkovsky, right before he died, figured out why. And he published it with one student, and nobody ever seems to have cited the paper where this was published. And they did not give a proof in the paper. Um, and nobody seems to have talked about this. So I will try to give you a sense of why this is the case. Why is this important? All right. Go back to the Sharkovsky order. If you have a map that has a period 3 orbit, you're guaranteed to have chaos. I claim also that you will also have a homoclinic in a period 3 orbit. And in fact, if you have a 2 infinity orbit, you're going to have a homoclinic.
Sorry, could you repeat what the exact definition of a homoclinic was?
Yep. So um, basically, you want a trajectory that starts and ends at the same place.
Okay.
And think about what that means. Let me do another diagram here. So if you want it to start and end at the same place, it probably should be at a fixed point.
Mm-hmm. That makes sense.
So in order for otherwise you're not going to converge to it by Banach fixed point theorem or by the Brouwer fixed point theorem. You're just not going to converge to it if it's not a fixed point because you have a continuous map. So if you're converging to a point, it must be near the bisectrix. Right. So if you're converging to it, you got a sequence that goes like here, 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 and it converges to this. So necessarily, uh, you need that this point maps to this point, which means it's just above the identity line, and then the next gap is about the same distance, so about the same distance above the identity line, and then the next distance is less far, so it's closer to the identity line because you're jumping further less far to the right, and then it keeps getting closer and closer to the identity line, so it must be a fixed point that you're converging to because you can look at the gaps between the successive iterates. That kind of makes sense.
Mm-hmm.
Okay. So we have established that these trajectories that start and end at the same place need to be at fixed points. So we can just look at what it means to end at a fixed point. Well, there's two ways to end at a fixed point. You could actually jump directly onto the fixed point, in which case you have a map that looks something like this, and you have a trajectory that starts here and then just jumps directly onto the fixed point and then stays there forever. That one's trivial. Or you have a stable fixed point, and so you have your map uh, locally is within this cone. So like this cone, that's what I mean. So that the derivative has absolute value less than 1. And so, like you'll jump to it and then you'll go here, and then you'll spiral in and converge. Or if it's coming from, uh, if it's sloped upwards, let's see, is that possible? Something like this. It's still within the cone, so we're good, but it will converge in such fashion as this. Oops. Let me make it more like that. I'm being stupid. Like that, maybe. Then you'll do this sort of thing. And you'll converge asymptotically, but never quite reach it. Unless you're perfectly flat right beside it, in which case you'll jump right onto it. But assuming that the derivative is actually non-zero, you will only asymptotically approach it. So those are the two cases. And it doesn't matter what happens over here because we're not even jumping on from that direction. So you could actually even have a tangency, something to this effect. Oops, I've been a little stupid in drawing this. So some kind of tangency where you just touch it and you peel away. So that would work. But in this direction, you would be unstable. So this is the nicest case actually because this gives you a. Um, I take that back. This is not so nice. This is one of two or three cases. It's one of two cases for the what's called omega limit behavior, which is how you arrive at the fixed point. So you want a trajectory that starts and ends there. So I'm saying there's two ways to end there, one being jumping directly on and the other being asymptotically converging. So let's study the case where you jump directly on. So let's say you have a fixed point right here. And is it possible? Let's see. So I jumped directly on it. So I came from over here, let's say. This is the pre-image. And then I want to wonder, is it possible? How can I get back to it in backwards time? How could I have come from the fixed point? Well, firstly, if I'm at the fixed point, I can't escape it, right?
Yeah.
I can't come off of it because it just maps to itself. So we need to have come from nearby it at least. So let's say I came from nearby it right here. And then, maybe I jump down to here and then I jump over here and then I spiral out unstably. And then maybe I end up coming over to here. This seems like a reasonable candidate for something that looks like a trajectory that starts super nearby the fixed point and ends up jumping right onto it. So it seems like a candidate for something like a homoclinic. And the map for this might look something like this. Oops, not quite. Let's go right through the fixed point and go through this. So a parabola, that's fine. Okay. So um yeah, so what are the preimages of this point right here? This could have come from two places. It could have come from right here or over here. And what that means is if you started right here, you would go here and then you would go over here. Or if you started right here, you would go here and then over here. And you end up with the same end behavior. So let's just look at this one. Well, you came from here and went there. Uh, Now there's two preimages at this point, namely here and here. Let's go with the right side one. Just assume that we came from there. Well, that's fine. We would have come from right at this point. Then assume we came from here. We have to have. Well, we could have also come from over here. But just assume we came from here, and then you can imagine we came from an arbitrarily long trajectory leading out from super close to the fixed point. as close as we want to have started to it, we could find a trajectory that eventually jumps right back onto it in this way. Does that seem reasonable?
So far.
Okay. So this is what we call if you take the limit of such a sequence of trajectories, you get what's called a homoclinic orbit, which is not a true orbit, but it's a limit of a sequence of orbits. Because you have to start it somewhere for a particular orbit. But this one doesn't start anywhere. It asymptotically back in time converges back to the fixed point, but doesn't ever actually start anywhere. But we call this a homoclinic. So hopefully this makes pretty good sense. Now I've written some computer algorithms based on the work of this guy named Victor Avrutin and Irina Sushko, which take uh, maps like this, 1D maps, and they locate homoclinics. They find homoclinics. They tell you where they are if they exist, and if they don't exist, then they tell you that they don't exist. It tells you that they don't exist. And it's a pretty efficient algorithm. They published a paper in Nonlinear Dynamics, I think was the journal, showing how to do this. And so I implemented it, and I've got a GitHub repo for doing it, and it's kind of nice. Um, but the key here is these things are very fundamental. It turns out that there, let's see, anytime you've got a map which has Sharkovsky order of to infinity or greater, you have a homoclinic. And if you have a map which has less than to infinity, so like some 2 to the n, Sharkovsky order, then you're guaranteed to have no homoclinics in that map. Hmm. It also turns out that if you have a homoclinic, then you are guaranteed to have chaos in the map. Just maybe not a measure non-zero set on where the chaos is occurring. It may not be um, it may not be dense, so on. Now, the other kind of homoclinic is one where you don't jump directly back onto the fixed point. So what that might look like, you need the fixed point to be unstable, otherwise nearby trajectories can't go away from it. So you can't ever get far enough away to have a homoclinic. You just go straight towards the fixed point. So in backwards time, you don't go towards it. So you need it always to be an unstable fixed point. But the other way it can happen is that if you don't jump right back onto it, but instead you have it unstable only on one side and stable on the other side, then you can. So this is the stable side, and this is the unstable side. And so you need to escape from the unstable side. And let's say you have the following behavior. Let's see, being dumb. You can have a trajectory that does this sort of thing. Uh, I need to go a little higher there. Sorry. And this side needs to go higher as well. So this should behave in this fashion. This jumps here, then it jumps over here, and then you're stable. Uh, I've drawn it stupidly again. So it jumps down to here, and then down and converges. So this is a homoclinic that I like to call omega infinite because the end behavior is not finite. It doesn't converge to the fixed point instantly in finite time. It only converges asymptotically in both directions, both alpha and omega in the limits. So these are the two ways you can get homoclinics in a 1D map. Now, Sharkovsky, right before he died, published this paper, and he gives this result about these homoclinics. And he says the following. He comes up with a nomenclature for homoclinics, where he calls what I've been calling homoclinics, he calls them one homoclinics. And he gives 3 equivalent conditions. So this is due to Sharkovsky and Fedorenko, his PhD student, I believe. Maybe not his PhD student, but some collaborator. So this okay. So the existence theorem goes like this. If and only if there's 3 conditions that are equivalent. One is you have a one homoclinic on orbit on an interval. Okay. That means somewhere in a map you have a one homoclinic orbit to a fixed point, and that orbit, because it must start and end at the fixed point, and for any particular starting value nearby the fixed point, it must have finitely many points in the orbit unless you have a omega infinite homoclinic, in which case you can lop off the end of it too, and just say, okay, once we get close enough coming back, we can stop there. You have a bounded orbit. You're always guaranteed that for any homoclinic. Okay, we're back. So, yeah, if you've got a one homoclinic on an interval, you're guaranteed this weird thing about nesting intervals. Like, I don't care about this result. Tarkovsky thought of it as natural, but I don't see it that way. I mean, it was natural in proving his result, yeah, but it's like it doesn't extend to the rest of the theory very well in a natural way that I can see right off the bat. But what was interesting to me from the paper was that he gives this really nice condition, which is the if you have a one homoclinic orbit on an interval, say the interval is A to C, oops, A to C, then um, and let me not do that. Let's do alpha to beta. Then there exists. So if you've got a homoclinic in here, you're guaranteed to have 3 points in ascending order: A, B, and C. You don't know anything about the spacings between them, but the map should send A. So the map should be f of x, and it should send A. It should do one of the following 2 things. It should send A to um, C, B to A, and C to C.
This is for 3?
Nope.
No.
Yeah, 3 points. There
Okay.
should be 3 points that get mapped by the map in this way. Or A to A, B to C, and C to A. Okay. And what does this look like in terms of a map? Well, the first configuration is I send A to C, and I send C to C, back to where it was, and I send B to A. Okay. So let's draw the map. And in fact, this is an equivalent condition. This guarantees the existence of a one homoclinic orbit. Okay. So in particular, I want to pick out 3 points. I want to pick out A, I want to pick out B, and they have to be in order, left to right. And I want to pick out C. And let's do it on the bottom axis instead. A, B, and C. And so considering the second case, right? Well, let's do the first case first. So I'll draw my bisectrix, and we'll do A goes to C, B goes to A, and C goes to C. So I've done my bisectrix. So A goes to C. C goes to C, so that's a fixed point of the map. A, if you start at A, you have to end up at C. So you have to have that being right here on the map. And B has to be sent to A. And so it has to map to right here, so there. Because it needs to go over to here. Okay. If you have this, you're guaranteed a homoclinic. No matter what map I draw, as long as it's continuous on this interval, it will have a homoclinic. I've drawn that a little bit stupid. That wasn't quite a function. This will have a homoclinic on it. I can find it very easily, and it will be a homoclinic to this fixed point. You see it?
Hmm.
Guaranteed to have it, no matter what. And that's a two-way implication. Now, the other case is for the other permutation, which was not quite the same, but in the spirit, it's the same. You label A, B, and C. Then now A is the fixed point. So it lies here. C gets mapped to it, so it has to be here, and B has to be in the pre-image of C, so here. And they don't have to be perfectly spaced out. It could, in fact, be something like this. So, this might be a trajectory that, or a map that looks something like this. But it could equally well just be something like this. A, C here, and then B's right here. Who cares? As long as you have A being a fixed point or C being a fixed point, doesn't matter. But if we choose A to be the fixed point, then you have to have C being on the same horizontal line as A. And going back to where C came from, you have to have B being a pre-image of it. So whatever height the C came from, B has to be on that line. Doesn't matter where. So if I now draw a map that satisfies this, then it's guaranteed to have a homoclinic. The homoclinic might look something like this. Okay. So this is really fundamental. Very precise result, not hard to interpret. Very easy search criteria. And he extends the theory of homoclinics up in a PowerPoint that, or like a Beamer presentation he gave right before his death. extending the Sharkovsky ordering to give something called the Sharkovsky stratification. Let me see if I can find that real quick. So I can talk about what one homoclinics and two homoclinics and so on are. So defining n homoclinics is kind of easy. It goes up in a natural way. Oops. So you saw one homoclinics. It's a homoclinic to a fixed point. So a two homoclinic would be a homoclinic to a period 2 orbit. So you can imagine that you have a period 2 orbit in a map, something to this effect. Let's do a small one. Okay. The map necessarily must pass through the bisectrix at some point between the 2 points on the period 2 orbit, and then you could have a homoclinic to this. Now, what would that look like? Well, you can imagine that it jumps. There's two cases. You could converge in forward time onto the periodic orbit, but never quite reach it, so you're asymptotically converging. I have messed up again. Being stupid. Yeah, so period 2 orbit, you can have a homoclinic to it, which means a trajectory that takes a detour from it and comes back. So some kind of divergence from it, then returns back to it and converges. So you can either converge asymptotically, or you can jump right onto it. So we'll just study the case where we jump right onto it because that's easier. So jumping right onto it looks like, we're going to use orange. So maybe it comes from over here and jumps directly onto the bisectrix and then goes around in this pattern. But it comes from somewhere. Let's say it goes out on a, what do you call this? Not discouragement. What's the term for this?
What?
When you like go away for a while and then come back. I keep forgetting what this word is.
Wait, are we being recorded or no?
Yeah.
Okay, okay.
Not a detour. What is the word? Starts with a D.
Deserted.
Deviation.
What is it? Jaden said a word. I didn't hear it.
Deviation. I'm not sure. There's a few words I can think of.
Maybe so. I'm thinking of like in Monster Hunter when you like leave and then come back after a while or something.
Disembark. No, that doesn't work.
You could say a disembarkment. So the trajectory has to have disembarked from a neighborhood of the homoclinic. It can't have come, or sorry, from a neighborhood of the period 2 orbit. It can't have actually come from it directly being on it because once you're on the period 2 orbit, you're periodic and therefore you just stay on it in forward time. But you can disembark from a neighborhood of it, which might look something like convergence in backwards time, asymptotically, like this. Now, what would the map for this look like? Well, the map has to include this portion that has the period 2 orbit on it. But then it also must include these points at the corners of the cobweb. That's sufficient. This has a 2 homoclinic. It's a homoclinic to a period 2 orbit. Okay. Now, this is an exterior 2 homoclinic because the homoclinic lies on the exterior of the period 2 orbit the entire time. And when I was studying this, there was some distinction to be made between period 2 orbits having exterior versus interior homoclinics, or mixed type, and they actually have topological consequences. And this relates to the chaos that you end up generating from these things and where they slot in due to the Sharkovsky stratification.
Wait, could we continue? I'm sorry to cut in, but
You're good.
I gotta stop for a bit. Yeah.
Okay, that's fine. But yeah, you get the main gist of it, like the ordering thing, and then where the homoclinics appear is the essential idea. Okay, see you.
All right. See ya. Thank you.